Second main GFG question, unique path in a grid. So basically we are given a 2D matrix and it has dimensions n and m which may not be same, and basically we have to start our journey from the first position and we have to go to the last position. We can either move right or we can move down. We cannot move to a place where there is one. Basically one is acting as an obstacle here. So from 0 we can move right or down. That is fine because both are zeros, both are free places. Then also from this second position, like from this position we can move to here, then we can move to here, then we can move to here, and similarly from this we can move down, then again down, then right, and then right. So we have to reach this last index n minus 1 comma m minus 1 if you consider zero based indexing. That is where we have to reach somehow without being blocked by 1, and we have to return the total number of ways in which we can reach that position. So here there are only 2 ways which are mentioned here. So whenever we have something like this, find all the total possible ways and all, you strictly directly go to the backtracking and DP, right? You look at the constraint first. The constraint here are 10 raised to 3 for n and m. So total combining them is 10 raised to 6, but if you consider it, it is 10 raised to 3. So if the constraint are around 500 at max, then there is a possibility that backtracking solution might get accepted. But here the constraint are 1000. So you have to implement a DP solution. But still, I mean, I follow this practice, you may differ, but I generally prefer to write backtracking first and then I convert that to DP because I'm not that much comfortable to write directly DP code. So I'm also going to explain you my backtrack version first. So first of all, let's see. This is n and m, right? Here we are defining the sizes. Now also, oh yeah, in this case, I forgot to mention. If the first block, if the first position is having 1, we cannot move. Or if the last position is having 1, we cannot reach the last position. So these edge cases are handled in this line. We return 0. What is 0? There is no possible way of starting or reaching the end. Now I've defined a count variable and I just call my backtrack function, which is going to count all the ways for me, and then I return my count. So how is my backtrack functioning? I'm starting from the 0, 0 position, and I'm also passing nm and this grid basically the given in the question and the count variable. Now if I actually reach the last position, then I will increment my count. Now here I'm not considering whether the last position is 1 or not, because that is already handled here in this edge case, right? So this last position will always be 0, so I don't have to write that condition again. So if you can reach somehow to these indices, you increment the count and you basically return. It doesn't return anything, so void. Now this is commented, right? Now there are 2 cases. If we can actually access that particular index, means if we go down, if there is a row to get down, right? I is less than n minus 1, right? We can go till I is less than or is equals to n minus 1, right? In any matrix. So here I'm considering only less than because I'm incrementing the I by 1 here. That's why that condition to not get that index out of bound error. And this grid of I plus 1, that the index that I'm going to access is not a block obstacle. That is also I'm checking. If both the conditions are fine, we can backtrack there. And same goes for the right part. The first line of code goes down and the second line of code goes for right. Now this backtracking solution completely works, but it gets TLE, right? So you have to convert it to DP. Now from backtracking, it becomes a little easier to convert it to DP, because if you directly convert to DP, you have to determine like what kind of vector do you take, 1D, 2D, 3D. But you generally take what arguments are changing. You observe what arguments are changing. So the argument that are changing, you generally pass on this backtracking function. The changing argument here are I and j. So this gives you the hint, okay, I have to take a 2D vector. This might sound so simple, but I'm not that good at DP yet. So now this is a DP function, although it is stated as backtracking, yet I have not changed that, but it's a DP, it's converted now. So what changes do you do when you convert a backtrack function to DP? First of all, you change the return type from void to integer. You don't do that count variable. You don't take an extra count variable. Here I'm passing the DP array instead of count variable. How do you initialize the DP variable? I mean DP array. So here you can see, just for the safety purposes, I have taken n plus 1 and m plus 1 here. and I've initialized it with -1. All these lines are same. This is just size initialization. This line is for handling the edge cases, and we can directly return our function because we are not taking any count variable. This function is actually going to return the answer itself. Now, what is the function here? This line, same as backtracking, right? This line, now, instead of here, you can also write like this in the DP function. But instead of doing that, I've checked these conditions globally. I mean, both at once, right? That if I mean, this is the condition, the thing that I commented here, that is what it is checking. Basically, we should not get out of bound, or the current place that we are at is an obstacle, then we return 0, right? Now let's go further. If our solution is already calculated in the DP, then we return from this stuff. This line prevents from getting a TLE because it solves the overlapping subproblems issue in the backtracking function. Now what we return? We return this summation of this line is going down, and this line is for going right. Now I have not checked this conditions here, right? Because I've handled it here, the obstacle one, and this index out of bound one is checked for here, right? If any of this fails, you directly return 0. Okay, so this will work. Let me submit this. All right, you will find this in the GitHub link in the description. Thank you.